Okay, here we go. Let's go through all the particle motion questions that have been asked in the past couple of years. I think there are about 10 of those, 10 of these, so shouldn't take too long. These questions are pretty repetitive and similar. Usually we'll be given an acceleration vector in this form. We'll be given initial position and velocity values for v of 0 and r of 0, and then we'll be asked for the position at a certain time t. And again, it's not necessarily time in these, but given that we're using acceleration, position, and velocity, it kind of sort of is time. But really, you can just do this with um, some parameter t. You don't necessarily have to think of it as time, but it definitely helps a lot. So in every step here, excuse me, I'm not going to be writing in any of the c's, all the plus c's, because really when we do these integrations, when we go from a of t and we integrate to v of t and then integrate again to r of t, technically we should have plus c's on the end, and then we adapt those plus c's to fit our initial values. But in my explanations, that's just going to be implied because it's a step that the plus c's essentially disappear as soon as they appear. So we see that our a of t in this first example is 2 negative cosine t 3 over 4 root t. And so we can integrate this to find our v of t, which will be 2t. And I'll just do this each step of the way. For t is equal to 0, for t is equal to 0, v of 0, our x component, should be equal to 1, so we'll add a 1. And then this is going to give us negative sine t, and this already matches. So our c is 0, because when we plug in 0 for this t, we will get 0 out here because the sign of 0 is 0. And then over here, this is it's too late. It's too late for this. This should be 3/2 root t. Is that right? 1/2. Yeah, okay, yes, that should be correct. And then again, we don't need to add any constants. Our plus c is equal to 0, because v of 0, this thing is going to work right there. So then integrating one more time to find our r of t, we will get t squared plus t, and then we see that r of 0, our x component, is equal to 0. So our c is equal to 0. And then over here, integrating, we will get cosine of t. Well, the cosine of 0 should be equal to 1. And so our c in this case is yet again 0. And then finally, integrating, we will get 2/3 times 3/2 t to the 3/2, or just t to the 3/2. And then we see that r of 0 for our z component is 1, so we're going to need to add 1. And then they're asking us for our value of r of t for t is equal to pi, so r of pi is going to be pi squared plus pi negative 1 pi to the 3/2 plus 1. And we see that we get that answer in answer choice A. Okay, a much simpler version. That was a little bit of a scary start. We're just going to do the same thing, except here we're dealing with I, j, and k forms of our vectors. So that's something to note. And in fact, I'm going to rewrite these because it's very easy to miss little things. So we have a of t, and this is equal to t1. We have v of 0, and they're saying that's I and negative j, so that will be 1, negative 1, 0, because there's a 0k component in there, it's just not showing up. And then we have our r of 0, which is actually hiding in the text here. It says our particle starts at the origin, so r of 0 is going to be 0, 0, 0. and we're supposed to find its position at t equals 1. So let's integrate. So our v, it's a hilarious v. It's absolutely terrible, but we'll roll with it. V of t is going to be t squared over 2, and then we see that v of 0 is 1, so we need to add 1, comma, t squared over 2 minus 1, and then t. And we can check this, but my changes have made this initial value happen for us. So then integrating one more time, r of t, we're going to get t to the, not to the sixth, t to the third over 6 plus t, comma, t to the third over 6 minus t, comma, t squared over 2. And we don't need to add any constants because we are starting at the origin. And then finally, we are finding our position at t equals 1. So r of 1, that's just going to be equal to 1/6 plus 1, which is 7/6, and then 1/6 minus 1, so -5/6 and 1/2. And we see that in answer choice D. Let's suppose that a particle has this acceleration with an initial velocity and an initial position, and we're asked to find r equals 1. This is feeling very similar already to last time. So let's integrate. We're going to find that v of t is 1 over t plus 1. And let's see, do we need to change anything? Well, for t is equal to 0, this is equal to 1, so no. Then over here, we're going to get 2/3 t to the 3/2. And yes, we will need to add 1 to that to match this for t is equal to 0. And then for our final component, oh, not with the eraser, 2t plus 1 is going to meet our requirement here, adding 1 for our constant. And then finally, our r of t, we're going to get as ln t plus 1, and then our constant, well, for t is equal to 0, ln of 1 is just 0, so that matches. And then we are going to have 4/15 t to the 5/2 plus t, which will match this initial value yet again, and then t squared plus t also matches our initial value. So now, not f of 1, we want r of 1, and we're going to find that that is ln 2, comma, 4/15 plus 15/15, which is 19/15, and then 2. And we have gotten answer choice number, sorry, I'm just, okay. Yes, we're good. I was just checking some of my initial value. I got scared with this plus 1 over here, but we're good. So we get answer choice B. A particle moves with this acceleration, and let's write this in the form that's easier to kind of see, which is a of t is equal to, well, our I component is 0, our j component is 0, and we have e to the t as our k component. And we are told that our initial velocity is 0, and that our initial position is, I'll write all this out. We have v of 0 as 0, 0, 0, and r of 0 as, well, our I component is 0, j component and k component are both 1. And we are ready to go. So integrating, we're going to find that v of t is 0, comma 0, comma e to the t minus 1. Because for t is equal to 0, we're going to get 1, and we need our z component to be 0. So we have to add a constant of -1. And integrating again, r of t will give us 0, 1, e to the t minus t minus 1 because, oh, sorry, is there a minus 1? I should actually check myself. E to the t minus t for t is equal to 0 is going to give us 1. And so we don't need a constant there at all. And we are looking for the position of our particle at t equals 2. So r of 2, we know that we're ready to solve this because all of this has been adapted to all of our initial values, is going to be 0, 1, e squared minus 2. And that's answer choice A. A traveling particle has a position vector given by this thing over here, and we're supposed to find its speed at t equals 1. Well, we know that speed, it's an S with a subscript p, is going to be the magnitude of our velocity vector at t equals 1. So in this case, it's the magnitude of v of 1. And we know that we don't have to do any fancy initial value stuff with this. All we have to do is take a derivative. So v of t is just, oh, but it gets a little messy, so I'm going to need some more room. V of t is going to be cosine t minus t sine t, then sine t plus t cosine t, and minus 2t. There, okay, now time for a magnitude, and this is going to be an enormous, doesn't need to be that tall, but it looks fancier, because our magnitude of this thing is going to be all of these components squared, and we're going to take the square root of that. So this is going to be cosine squared t minus 2t sine t cosine t plus t squared sine squared t plus sine squared t plus 2t sine t cosine t, almost made it in one line, plus t squared cosine squared t plus 4t squared. Oh, God, okay. So let's cancel some things out. We have a cosine squared t and a sine squared t. That's just going to change to 1. We have a minus 2t sine t cosine t and a plus 2 sine t cosine t. And then over here, I'll rearrange this to make this a little more legible. We have a t squared cosine squared t plus t squared sine squared t. We can factor out a t squared from that. We will see that we are left with a t squared, which we can add to our 4t squared, and this whole thing simplifies down to 5t squared. Okay, and we are finding our speed at t equals 1, and so that is just going to be one enormous square root with a very, very small 6 in the middle. Okay, back to kind of more normal questions. We know how to do these, so let's just do it. V of t will give us 6t plus whatever our constant has to be. Well, v of 0, our x component is 0, so we're good. 3t squared, integrating there, and we're also good because we want 0. And finally, we're going to need a constant of 1 here. We integrate 0, we get 0, we need to add 1. And our r of t is going to give us 3t squared minus 1, actually, because we're given r of 1, and so r of 1 here, well, that's going to give us 3, so we need to subtract 1 to get 2. And then over here, t cubed, r of 1, that's already good, so we don't need to add anything. And then we will get t plus 1 over here to get our 1 plus 1 for 2 over there. And we're looking for the magnitude of the position vector at t equals 2. And we can just plug in 2 before we do anything else. We're going to get our x component is going to be 2 squared times 3, which is 12 minus 1 is 11, comma, 8, comma, 3. And so this is going to be the square root of 121 plus 64 plus 9. 121, 64, 9. We are going to get 14, 9, 1. So the square root of 194. Oh, this is an extremely weird one. It's a very sneaky question. So, and you kind of have to almost know some basic physics to go along with it, which is a little cheaty. Uh, but we'll get through it. So we're given the position function of a space shuttle, and we're given the coordinates of the International Space Station. And we are told that we're trying to dock with the space station, and we're trying to turn off our engine so that the space shuttle coasts into the space station. A little spoiler here: we end up hitting the space station pretty hard with our many thousand pound space shuttle. So not sure if they're really sending the right message here, but hey, at least the two things hit. So we see that the space shuttle has fixed coordinates. That's something to note. And we also know that having our engines on, all that's going to do is kind of turn our acceleration on. So we have our R of t, which is informed by our V of t, which is informed by our A of t. So when engines are on, our A of t is on. So whatever acceleration we get from this position function, that will only be the case when our engines are on. When our engines go off, our our V of t will be stuck at whatever our A of t brought it up to right before turning off. So starting to solve this, we see that our R of t is t squared negative t squared negative t 6. And so our v of t, oh my god, I'm erasing everything. Our v of t is going to be 2t negative 1, 0, and our a of t is going to be 2, 0, 0. 2, 0, 0. Okay, the handwriting's a real struggle this evening. And this is interesting. So we see that our engines are only accelerating us in the x direction, which tells us something else. We see that the space shuttle's y coordinate is negative 5, and we see that our position function, which will not, and our velocity function will not be changed at all by having the engines on, is negative t over here for our y component. And so we know that at t equals 5, we're either docking with the space shuttle or not docking with the space shuttle, because that is the only time where, if our trajectory is going like this, and here is our ISS, that is the only time that our x coordinate is lined up with the ISS at t equals 5. And so all we have to do is accelerate enough in the x. Did I say x coordinate? If I did, I meant y coordinate. We have to accelerate enough in the y direction to, well, it's going to look more like accelerate enough in the y direction so that we can coast into the ISS at t equals 5. So this is important because it tells us that we cannot be shutting off our engines after t equals 5. That wouldn't make any sense, because we see if we plug in t equals 6 or t equals 8, our position function, our y component, will have already passed the space shuttle. So those guys are no good. What happens if we shut off our engines at t equals 0? Well, if we do that, then our velocity for the rest of our trip is going to be 0, comma, -1, comma, 0, which means our position function is never going to move um, in the x plane, and so we're never going to align both of our coordinates with the space station. What about t equals 4? Well, if we shut off at t equals 4, uh, that means that our, let's see, 4 t equals 4, because these are our real two like candidates here for a correct answer. So we're actually going to write stuff down for it. For t equals 4, v of t at t equals, oh sorry, well really it's v of 4 would be 8, -1, 0. And we'll see that r of 4 will be 16, -4, 6. And so we see that this, sadly, is also no good because we've lined up our x-coordinate, but we've lined it up a second too soon. We've got 16 in both the space shuttle and the space station's coordinates for their x-coordinates, but we're a second too soon because we know that we're limited by our y-coordinate drifting in there. And so D is out. What about t equals 2? So for t equals 2, our velocity is going to get up to 4, -1, 0 before we cut our engines, and our position is going to get up to 4, -2, 6 before we cut our engines. And when we cut our engines, this velocity is going to stay the same, and so we're kind of, I'm sure there's a way we can do it mathematically, really, but we're just going to, well, it is still is mathematically, but we're just going to manually work through the last 3 seconds. So if we do 3 seconds more of this at this velocity, all we have to do is multiply this velocity by our delta t, which is 3 seconds, and add it to our position. So if we do that, we will see that we will get r of 4. Well, our x-coordinate is going to be 4 plus our v component here times 3, which is going to be plus 12. We're going to get -2 minus 3 here, and we're going to get 6. And we see that this works out perfectly because this is an r of 4. Sorry, this is r of 6. And everything over here that says 4 should also say 2. I forgot to change that. 2. There we go. And so at t equals, this isn't 6 either, this is t equals 5. Oh my god. So r of 5 is equal to 16, -5, 6, which is exactly what we wanted. Okay, final question. A particle has the position r of t with this acceleration and some initial conditions. Let's blaze through this question in honor of it being our last one. So we see that a of t is equal to t 0, 3t squared. We can integrate, and we will get t squared over 2 plus 1, comma 1, comma t cubed plus 1. And then we can integrate again to get our, so this is v, we can get our r, which will be t cubed over 6 plus t, comma t to the 4th over 4 plus t. And we can find r of 1, that's just going to be 7/6 plus, sorry, not plus, comma 1, comma 5/4. And there we go. And we're done. I hope there's someone out there who's extremely bugged by the fact that in every single video I consistently put parentheses and angle. I think it's the English that call them angle brackets. I don't really know what to call those things. They're not carrots. They're like sideways carrots because that's a carrot. I hope some of you are extremely bugged by it. I should be more bugged than I am by it. So please feel free to dislike this video in honor. But hope this was helpful. It's very repetitive, but kind of satisfying. I don't know, something about these problems, especially the space shuttle one. It's a really rude problem for them to give, but it's really kind kind of cool to solve in the end. Um, but I don't know really what I'm talking about. So hope yeah, hope this was helpful.